Have you ever wondered how we map Mars? It may be a bit of an odd question initially, but first of all, I've totally wondered about that before. And two, we definitely are mapping Mars extensively, actually. My guest today is Dr. Fred Calef III, and he has the unofficial title of
the keeper of the maps.
When we send rovers and landers to Mars, we need to know where to send them. It's as easy as that. And for that, well, you need maps. And that is Dr. Calef's job. And to do that, you need to go all the way back to the drawing board.
Which way is up? Which way is north? Where's the center of the coordinate system? What coordinate system are we going to use?
If you've ever wondered how we map another planet, bodies, this is the conversation where we talk about it. This episode is sponsored by Kermap. They're behind Nimbo, a very easy-to-use platform showing beautiful cloud-free composites of satellite images over time around the world. I talk a lot about satellite images on this podcast, and that's probably no surprise, but I also often want to show people, especially those around me who aren't as familiar with satellite images, what they look like, and maybe more importantly, some specific changes over time. Nimbo is one of the easiest and simplest platforms out there to do this. Anyone can really just use it. In just a few clicks, you can make a render and a time series animation and easily compare images over time. They make monthly mosaics, stitching Sentinel-2 optical images together, creating a catalog over time that you can easily explore. You can log in at maps.nimbo.earth for free and just start browsing around, comparing images over time and just exploring the world, either in 2D or in 3D with elevations and mountains. I do want to highlight this. It is really easy to use. In a couple of clicks, you can export a GIF of change over time or individual images. They've made the UI incredibly simple, so I recommend you just go ahead and take a look for yourself at maps.nimbo.earth or send it over to someone who you've been trying to explain what the heck satellite images are, as anyone can really easily use this. This is, in my opinion, the biggest benefit of Nimbo. So head over to maps.nimbo.earth to try it out for yourself. And thank you to Kermap for sponsoring this episode. The way I like starting these conversations is I like asking people how they would describe themselves. So I'm quite curious, how would you describe yourself?
I would just say I'm a mapper, even though I would probably also say geologist because of what I studied and then my interest. Technically, my day-to-day is more mapping than anything else. And I know now it's like geospatial analyst or, all sorts of fancy words. But I think, the map, the thing that you make is what you do. And cartographer, I suppose I could also say, but I'm per se don't have a formal cartography background. I've had a couple GIS classes, but that's it, so I don't have this kind of formal training. It's more learned, and part of a geologist is making maps, but I've kind of glommed onto that. So yeah, mapper.
The maps that you work on, at least at the moment and for the past few years at least, they're a little bit different from the maps that most people might think of. You don't really work on maps on Earth anymore, do you?
I've been getting back into it. I do typically work on maps of Mars, specifically for the NASA Mars rovers, Curiosity and Perseverance. My first formal position at JPL was Science Application Software Engineer. However, on the mission, I was the keeper of the maps, which was just a title that was kind of like given to me offhand, and I just run with it because I think it's the best thing in the world. And it was also a transition to a very different type of mapping where, a lot of times I think maps of like, you take a lot of time, you build up some data, you make the map and you hand it to someone, right? Or you give them the data set or what have you. Mapping for a mission is very different. It's very day to day. It's very quick. And so you need accuracy in a short period of time and deliver products and maps themselves to people so that they can use it that day to plan where this mission is going to do their thing, right? So for a rover mission, it's where we're going to drive the rover, or what rocks are we going to do science on, what instruments are we going to use, and then prepare for the next day. And that cycle repeats and repeats and repeats. I go to work every day. I go to Mars. And I don't mean just like hype. Well, I mean, it is hypothetical, but in my brain, like I get to see the surface. I get to see rocks, rocks that you can pick up. and then like figure out where that rock is. So yeah, so it's mostly been in Mars.
I want to get into what it takes to map Mars, because I think a lot of the history of mapping, is on Earth. I mean, like that's where most
Right.
people were most of the
Yeah.
time. And so it starts with people physically going out there and then, starting to draw stuff manually on paper. We send explorers out and then they have specific goals to go out mapping. It's only very recently that we're able to uh, fly and then put satellites up there. And now we have, like, mapping is very much a, space engineering, orbital mechanics, and then software. That's what it takes to map stuff. And we have a lot of history of how we map. There's a lot of projections, like the name of Mercator. Like these are really old things. There's a lot of history to mapping Earth. But then when we go to Mars, it's a lot more recent. But we also start from a blank slate in a way. Maybe not. And so I just want to go over, like, starting really high level, like what does it take to map Mars? What are maybe some of the differences? And then we can kind of go from there.
To map Mars or any planet, you really are starting at the very beginning, to the point of the basic questions that we know for Earth, right? Which way is up? Which way is north? Where's the center of the coordinate system? What coordinate system are you going to use? Based on the spin of the planet, which way is positive east? What is east and west? So those basic things you have to figure out. And on Earth, we have concepts like sea level, right? Surprise, we're the only planet that has a sea, or at least well, that's maybe not true for Titan, but mostly, there's no water in the other planets. There's no liquids. There are different liquids. So Titan being interesting that it's all organics. It's like not oil per se, but it's like oil all over the surface. Not all over the surface, but in certain areas, there are big lakes. So anyway, so a fluid, but then you get into like air pressure. So, like where would liquid water form? And then you got to think about that. What's it like on a planet it's wholly, all its atmosphere is CO2, and it's super cold, and you never get water except for transient little bits. So deciding just where zero elevation is, where the coordinates are, how to divide things north and south, like that's the first part you have to do. Now, interestingly, the second part, because the planets are far away, I mean, there were originally, all the planetary geology or planetary mapping was done through a telescope, right? So you got a big telescope, you're looking at Mars, like the Lowell Observatory in Arizona, and you're peering through and you see a full disk, right? So, you're getting this per se orthographic projection, right, from space, and you're just tracing out features, and they're pretty crude. But that's only half the planet, right? Or maybe not even half. It's only close to that half. So until, but the planets rotate, so you start to get the other sides, and you start to push together what the planet is, and you decide which way north is, and then you have to pick a location to start a coordinate system, right? Well, where do you pick? Does it matter? You got to kind of figure out what the spin axis is, and then, divide it in half, and then just pick. Interestingly, so that's part of it. So there was that manual part, but then if you really want to map at a larger scale, things size of countries or states or what have you, or the equivalent, you've got to pick a feature, right? So you got to get spacecraft there that can actually collect enough information. So we did that with Mariner back in the 60s, and then later much higher resolution with Viking in the 70s. And higher resolution, I mean a few kilometers to hundreds of meters per pixel, which was pretty good back then. But that was all digital. It was all a video stream. Some of the first image processing software actually was built at JPL, where I work, called Vicar, Video Image something. But basically, it was just image processing. How to take and the reason it was video is because the original cameras were Vidicon. They weren't really cameras. They were like TVs. Like they would scan across an image and record, and basically like an analog video stream, and send that back to Earth, and then we would recreate it digitally. So they built those original digital tools. So we really started digital. Now, what people would do is they would form an image and they would print it out like an air photo, and then they would kind of do the manual thing, right? And they would put mosaics together. And a few years ago, we went through a bunch of cabinets, like we saw these monstrous mosaics where people were doing that old air photo thing, right? But the data was digital, and once we had enough compute power, then it went straight to digital. Then it just becomes basic mapping. The only thing everyone is like, oh, what's the special projection? I'm like, everyone on Earth, all you do is change the radius. And people have gotten so it is like I don't say call it a pet peeve, but all software, they bake in a radius for Earth, and that's it, right? They don't think about datums, they don't think about the origins. But planetary, it's just about changing the radius. And all the planets are basically have a central longitude and central latitude, a prime meridian. And on Mars, it's really interesting. They basically, there's lots of craters on the planets, right? Or at least on Mars. They picked a crater as small as they could go, and they called that Airy O. Airy is the last name of, like, it's Colonel Airy or Admiral Airy, who built the Royal Naval Observatory in Greenwich, England. So in some ways, there's this direct connection between Mars and Earth in that in that mapping sense, which I think is kind of fun. But we get better images, and then the center point of Area gets shifted by little, by meters, right? Because we're redeveloping the system, and then they're also the very high end of it, which I don't typically delve into, but it's like the photogrammetry, like do a bundle adjustment of like 10,000 images over the planet to reset the geodetic network to then establish your mapping base. We don't like to do that often. It's kind of been set for now since the Mars Orbiter Laser Altimeter, MOLA, which was a LiDAR instrument that they flew over Mars, got 600 million LiDAR measurements of the surface, and those were all kind of bundle adjusted and developed basically like the geodetic network. But we also tie that to imagery, and so there's every once in a while someone tries to go and redo a bundle adjustment. But it's a lot of work, and it's a huge effort. But we're getting pretty good. The accuracy on Mars, absolute accuracy is about 150 meters.
Right. So does that mean what does that actually mean? Like in terms of the coordinates that you can place properly?
Yeah, well, it's the absolute accuracy. So if you put an image fly an orbiter now, you have some idea of the ephemeris and the shape of the orbit, and you take an image of the planet and you put your finger on a rock and you go, where's that rock?
I see.
Well, it's going to fall in the coordinate system, but it's going to be plus or minus 150 meters, absolute.
Please tell me if I'm wrong, but
sure.
Some of the highest res imagery, I think, is high rise at the moment,
yes.
And it's half a meter?
It's quarter meter, 25 centimeters.
Right.
Yes.
And so, but I mean, I'm imagining like that's a huge giant zoom lens, so you can have probably just a very narrow swath, so we don't have the entirety of the planet mapped at that.
Yeah. The entire planet is mapped to about 6 meters per pixel. This is the context camera on the Spain spacecraft that HiRISE is on. So we have global coverage at about 6 meters per pixel. We have, I don't know what the number is currently. It's probably like 4% ish of unique coverage at the HiRISE level, 25 centimeters per pixel. So then you go like, well, how do you put anything on the surface, right? 150 meters is the difference between a cliff or a big rock.
That's what was my next question.
Okay, yeah. So a flat plane. So it all comes down to, well, two things, statistics and then relative accuracy. So if you put an image, like a high-res image on the surface, and it's like 6 kilometers across, and it can be tens of kilometers long, each of those pixels is off by about 150 meters, but pixel to pixel, the accuracy is closer to the resolution of the image. It's closer to, a meter or less, right? Or really sub-meter. So how do you deal with that, putting something on the ground? You either do it with statistics, you get a big enough area that you land in, and say statistically, if you land somewhere within 99%, you'll be safe. And that's by looking at size of rocks and looking at slopes. So you can.
Oh, so
you can,
sorry, you're talking about the context of like trying to land a rover.
Yes.
Okay,
Yeah.
got it.
Yeah. Sorry. Trying to land a rover on Mars or anything on the surface. You don't want to land on a rock, a big rock, sharp, pointy rock. You don't want to land on the side of a cliff. You don't want to land in the middle of a crater that's covered in sand because you won't be able to get out. So to deal with that inaccuracy of 150 meters, you can deal with it in terms of statistics. Say you cover this area with imagery, it's this percent safe, and you live with that percentage. Typically, it's upper 90%. We aim for that. But if you get enough images of high resolution and you mosaic them, then your relative accuracy within that image, is in the meter level. So the latest technology we use is called terrain relative navigation. And this is a cool part because then mapping becomes, it's more than just a statistical number. Like we just say this 150 by 40 kilometer area is safe, and they just land and you aim for the center and you wind up somewhere else. But if you really want to pinpoint your landing, if you want to land in I know this pixel is safe. So you do it this way. You take a map, you develop your base map to whatever accuracy you need to land. And then you put it on the spacecraft. And then as the spacecraft is landing, it's taking images and it's going, oh, took this image. I match it to the map. The second it gets a fit, then your accuracy becomes the accuracy of that image fit to the base map, which we can get down to around, the stated number is around 40 to 60 meters, which is great, better than 150, right? That keeps you away from big cliffs. It keeps you away from big craters. But importantly, so you basically you snap the spacecraft to the map. So you think you're here, you're actually here, and then they do the math to calculate where you land on the surface. But the cool part is we make the map that goes on board the spacecraft. So, distortion, distances, angles, all those basic things that they teach you in school. And you're like, yeah, the map looks good. No, it has to be super accurate. Then they get into the camera models and the distortion of the images and how to remove all that error photogrammetrically and then get a map that they think is as accurate as possible. And so you can do that relative snap to a base map, which then itself is accurate, and then you can land on it. Interestingly, so when Mars 2020, the Perseverance rover landed, because you have a map and it says, I'm going to try to land here, it sends back that coordinate. And so the robot lands, it says, beep, beep, I'm here. And we put the dot on the map. We go, okay, we know it's within 60 meters. And the way the robots work, the rovers particularly, you have two sets of cameras. One is called a hazard camera, and it kind of sits down low to the ground. It's between your kneecaps and your hips, somewhere in that area. So about half meter to a meter above the ground, probably closer to a half meter. Yeah, it's around 50 centimeters, 60 centimeters. And that's the first picture you'll get at that low level. The camera that's on the mast, and the mast is about 2 meters high, doesn't come up till later because the mast gets folded down. In fact, hold on.
Oh, this is cool.
Yes, I keep full scale models just because I can.
I love this. So this is for people that are just listening. This is like a Perseverance model.
Yeah. So if you have a roughly 1:20 scale model of the rover at your home, so the mast is typically folded down when it lands, and the wheels are pulled up close to the rover, and the arm is in, because you got to fit that whole spacecraft into this aeroshell, and it's only so big. So the first pictures that get taken are from the front and the rear, and they're very low to the ground. So you can imagine if you go anywhere and you take a picture at that height, right? You can't really see. You only see the features that are within a couple meters of you. You can't see very far. What you find, a lot of Mars and the moon's even worse, is that the surface is very fractal. in terms of like, you can be like looking at it from 10 kilometers high, and you can be looking at it 1 meter high, and the surface looks exactly the same. The moon is like horrible. It's just like, it's always craters and rocks. Like, and they just they're at all scales. Mars is a little bit better than that. But when you're at the surface, like, you can only see a couple rocks a couple meters away. And you might see like things in the horizon, but that's not going to put you within a few meters. And so we got this one HazCam image, and I'm looking around. I'm like, I don't know. It's that group of rocks. It's that group of rocks. It's that group of rocks. Like, I don't know. And then finally, the mass in the spacecraft comes up on the rover, and it takes a 360 pan in stereo, and we create an orthophoto from that. And then we can take that orthophoto and we can put it on the map, right? And we match basically the data from the rover to the base map at the 25 centimeter scale. So it's a bit of a big jump. It's 1 centimeter per pixel to 25 centimeter per pixel. But you capture enough features because now you can see out 20 to 40 meters. And so you can see things of positive relief like the crater rim, but you can also see things of negative relief like the middle of a crater. So you'll have a hole in your data and like, oh, well, that's a crater, and I can kind of fit my data in there. We wound up being within 5 meters of the pixel they picked. That pixel was 5 meters. So they literally landed on the pixel they picked, which was what they call it, like a population of 1, n equals 1. So like, all right, maybe they just got lucky, but wow, it was pretty amazing. But, the fact that map was that accurate, that was the important thing. And that to me was like, that put mapping to a whole nother level, because before it was just like, we said this area is safe and the spacecraft flies there and it doesn't care. Like, it has mechanics of like, oh, I have a radar range finder. I know I'm this high above the surface. Okay, start my deployment sequence, start to slow down, put out this much thrust for this long, and then you're going to land. It was very mechanical and, deterministic. Where now they have a map and it's a little bit stochastic. Like, we can land in these 100 spots that are safe, but not these other 1,000 spots. And we're going to pick that location on that map and fly to the map, which is just, to me, was huge. Like, suddenly, like, our maps weren't just like, yeah, I gave you a number and we're safe. It's, no, we need the map. It needs to be accurate. Are you folks doing the right thing? Is your projection right? Which is another story.
I watched so much stuff when the rovers were landing, Curiosity and then Perseverance. And I think like one thing I want to mention for people who might not be familiar, like, this is completely automated. There's like I think it depends, but like roughly a 20-minute delay between Mars and
depends on the day. Depends on where Mars and Earth is, but yes.
And what I mean by delay is like the distance for light to travel all the way there. So like, even if we had someone with a joystick and they were leaning it to the right, it would take 6 to 20 minutes to get there for something to actually turn right. So it's just not feasible.
Yeah, the ping is very large. You don't want to you don't want to do a land game with someone on Mars. You're always going to lose.
Yeah, that's a good point. We're not going to be playing planetary land parties anytime yet.
Maybe a very slow MPORG or something, very slow multiplayer game. Anyways.
Yes. But like, that makes it that much more impressive that you need to have all this system to be able to work, because it's really just hands off. Like, okay, right, well, the lander's should land in a minute. Oh, maybe it landed, maybe it crashed, and then you're just waiting. And then you hear back from it. Like, there's also that aspect of, it's not just, oh, we need that data so that someone can land it. It's, we need to load that data up. We need to load these algorithms up, the sequence, so that it can land on its own. And we need to be prepared as much as possible.
Yeah. So think of it this way. How fast can you georeference an image to a base map? Right? Can you do it in less than 100 milliseconds? That's what they had to do. And they did what they called 2 coarse coarse image corrections. Coarse in terms of like the resolution, like get you within 60 meters, and then for fine images, we got you down to this like 20 meters error. But literally, tens of milliseconds counted because they're coming down at, Mach 7, and they have to go to, meters per second in terms of vertical and horizontal velocity. And you have to make decisions very high up to start the landing sequence. So, you know, 80 milliseconds, locate the first image, locate a spacecraft. Next one, 80 milliseconds, 80 milliseconds, it just so fast. And to do that, you got to start to simplify how you project the image down and make some guesses. But yeah, it's super fast and just amazing the way that they process it down. And there's just, so you think like, well, how do you do that hands off? And we call it the saying is the 7 minutes of terror. And that's the time from when you start your landing sequence to that you're on the surface. And it's basically like it's hands off. There's no software updates. There's no course correction.
I want to come back to one of the things that you were saying about like, we have the coordinate now of like the one of the rover when it lands. And I was also thinking like, what do we mean by that 150? Like, how come we have this 150 meter accuracy if we have these 6-meter images? And my understanding is like, first of all, I need to remember that this thing that I take for granted all the time, which is GPS, we don't have it. And so you can't just be like, oh yeah, here's the location of everything that we ever know and how it's moving and all that stuff. Like it's back to how it used to be, which is like, if you don't know where you're on a map, you're lost.
Yes, absolutely.
And so this opens up like a whole can of worms of like, yeah, needing to find where you are. Like you just can't do it the way that we're completely used to today. And so I want to ask this question of, we're talking about sending humans to Mars or the moon or anything. Do you think like that would be how people would move around? Like, or do you think we'd need to send some sort of positioning system, or would it just be like image interpretation? I'm really curious about that, because rovers, it's someone, we're moving them pretty slowly, like we kind of know. But if we were to send people, we'd want them to go all over the place, I'm guessing.
Yes. So what we typically call localization, I guess that's a phrase that mappers use. So for the rover, we have a couple things that work for us. One is it doesn't go very far, very fast, although that's changing a little bit. The other part is we have time. So the way a typical planning for the rover goes is we plan what the rover wants to do during the day. We send it to the rover on Mars. The rover executes that plan over its day and then send us back the results. So we kind of have like this 24-hour loop where the rover can move, takes pictures, sends it back to Earth, and then we take that imagery and we, based on rocks that we see from orbit, compared to rocks we see on the ground, and we just literally just slide that map over. We just do a translation to say, okay, it's here. Grab an elevation point. That's where the rover is today. So that's fine for a rover every day. It's one spacecraft, right? Well, then we have Curious. We have 2 rovers, but still, like I just last week I had to. Everyone went to the eclipse to go see the eclipse in the United States, except for me. I was Team Loco, or Team Loco Solo, as I like to call it that day. Localizing both rovers, making maps for each, giving it to the science teams. That was a fun day. I didn't know which side of Mars I was on, but it's okay because it's just one thing that's, it's moved and it's stopped. Where if you can imagine sending humans to the moon, once they're on the surface, like they're walking around, it's not like you give them commands like walk 5 paces out the door, turn 30 degrees, walk 10 paces, how big is your pace, da 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 da. They're going to be kind of random. So how do you track them? There currently is no GPS on the moon. You can they've done some studies like using our current like Earth GPS constellation to try to look at how accurate you can get on the moon. But it's not super accurate because it's just not built for it, right? In the the orbit.
Yeah, for
You
sure.
don't always see all the satellites, or many. And then and also they want to go to the South Pole of the moon, which then you're talking high latitude, and you're still you're probably seeing less of the constellation because of other, obscuration of GPS satellites. So ultimately, yes, they have to have a solution. Personally, because they're gonna want to care about things like, where did I put my rock hammer? Uh, you know, where was that sample that I took? Where did I leave the rover? Like all these kind of basic things at a work site, they're going to be able to track. And modern work sites, sometimes they have drones flying overhead every day, and they're recording the construction, and they have laser theodolites, and base stations that they're recording everything. So I feel like they should have that on the moon. They're working on solutions, but I think it is critical that they develop something, because ultimately they're going to want to know where everything is. And you can imagine, you can have cameras take pictures every day. You can imagine a bunch of things that could help localize things, but it's going to become they're going to find out quickly that it's going to become important.
The early days of like in-car navigation was like before GPS, and so they used basically they use two things. They use dead reckoning, which is like knowing, like, okay, you moved, which is like how people navigated on boats, which is like, or airplanes actually for a really long time. Is like, okay, we're heading like this, heading north, for example, we're at this speed and we've been going for 7 minutes, therefore this is where we are. And so that's how people navigated for like most of history. And then once we knew where the road networks were, you just snap that to the road. I mean, there's no road, but do you think like dead reckoning like that could just suffice, or is probably not going to be enough?
I uh, I mean, that's kind of how they did it with Apollo. The
Right.
astronauts were just saying like, I'm approaching the rill. I've been walking this direction. I think they also had like kind of a grid system, and they would just kind of randomly call off like, oh, I think I'm in grid 37 West or some such thing. It'll work for a while, but I think it'll get very tiring. Like the first mission, there's 2 astronauts. They don't go that
Oh, I just meant
far.
like some automated system that just
Oh
is
yeah,
based
no.
off.
I'm sorry. Oh, you mean like an automated system?
Yeah, not necessarily like they're with a compass in their hand all
Right.
the time. Well, that's not going to work very well on the moon, anyways. But
Yeah.
um,
You so like the rovers have internal measurement units, IMUs, and they use that to do a dead reckoning. Like, I think I went this direction this far, this acceleration. They also do other things. They count wheel turns, and so
oh right, yeah.
right, so they count the wheel turns, and that gives you some version of distance. But they also take images, and they'll do like a little adjustment to help relocalize themselves, because they get a lot of slip. They say they drove 5 meters, they actually drove 4.8. So the images help them snap and correct for that stuff. But generically, they count wheel measurements, and the IMU gives you an acceleration and an angle. So they could probably do that, no doubt. The thing with dead reckoning is that the error accumulates.
Yeah. You need to
And there's no
recalibrate.
road network to snap to per se,
Yeah.
right? Literally, they have to make their own roads. But I think they, and you could say like, oh, I've reached this big boulder. Oh, I can see that big boulder on the map. Okay, that's a coordinate, right? And so then you
Yeah.
could start to adjust things. They can certainly start that way. I wish they would do something a little more accurate.
Yeah. Not as interesting.
But
Uh,
they just try to get the humans to the planet safely, and then they
yeah.
think about other things.
There's no well there's no, like, you couldn't use a compass on Mars or even on the moon, right?
I think the short answer is no. There's Mars doesn't really have a magnetic field. There's some remnant magnetism. I don't know if it would point towards something. It wouldn't be north. I mean, it would be magnetic north, right? Like whatever north is, right?
Yeah.
The moon, I think, is in the same boat. So no, you couldn't. I don't think you could use a formal compass on the moon. because there's not really a magnetic field. But what they do use is star trackers.
Right.
So you know roughly where you are on the planet. You see these stars, and that gives you an orientation. So
That's how
you can imagine.
satellites do it too.
Yes, right. Satellites do too. Yeah. So you can imagine that every like helmet has a star tracker on it, and it's just constantly looking at stars, I suppose, right? Or you have a station that, some kind of base station that's always looking at the stars and gets an orientation, and then or do some kind of radio telemetry of where you are, laser rangefinders. Like you can think of a lot of solutions that are not GPS, but they would require like coordination. A bunch of retroreflectors that you measure out, where they are, and then you laser them, all sorts of stuff like that.
That's so interesting that it just kind of goes to show how completely dependent we are on GPS and GNSS, I should say. Because it just makes everything so much simpler.
Yes.
Like we just totally take it for granted. Like, oh, where am I? You just pull your phone out. And this also a really low powered thing in your pocket just knows where you are all the time.
Yep. Constantly. A little too much. A little too well.
I want to nerd out on some of the mapping tools. I know that you so you were talking about you use some of a lot of the mapping tools. They have these assumptions around radiuses, which I never really thought that was a thing. But I know you use things like leaflet, for example, to just show. You use GDAL, to really go into it. How much effort is it to use these open source kind of off the shelf software and say, I'm going to have a different projection. I'm going to have a different coordinate system. Is it like a lot of just custom work on top? Or is it just like super easy to use all of those?
Both. GDAL is very good about projections. So, you can say the data is in this projection and you want it in this projection, but with the moon's radius or Mars radius, no problem. So GDAL is very nice. I certainly know, I do know that like the U.S. Geological Survey, specifically their, I would say astroplanetary, but that's not quite right. Anyways, their planetary division, they're very big into open source, and they've been working a lot with GDAL, and just mostly they're like big proponents of just like, we need a Mars projection. Can you please put that into your software, right? Or can you allow the software to recognize the Mars projection? So GDAL's pretty pure in that sense, like, because there's different versions of the planetary of Earth's radius as well, right? Anything from we went from WGS 72 to WGS 84 to whatever the next thing is. So GDAL is very great about projections. So it doesn't care. It just says, well, tell me what the projection is and I'll use it. Things like leaflet or open layers or, insert mapping software, open or closed source, they got an Earth's radius baked in. And it takes a lot sometimes to make them recognize what the actual planetary radius is. And then other tools have got their own Earth radius baked in. And so it's really difficult. That is the only problem we've dealt with. And, the one cheat you can do with leaflet is that it typically works in longitude, latitude degrees, right? So longitude, latitude, like as long as the planet's spherical, we don't care. Doesn't really care what the radius is. You just can't use like their measurement tools. So then you have to bake in your own solutions afterwards. And the other part is tiling. The tiling is if you abstract away the radius part, it's just a quad tree structure. It's just, this many squares and it goes down and down and down. You just kind of like take the Mars data per se, pretend it's Earth and just tile it up and then tell the software it's Earth, but it's not. That's a very simplified version of it. So sometimes you do that fakery, and other times, if you just do everything longitude and latitude, it's just like, well, if you want an Earth, you apply the Earth radius. If you want a Mars, you apply the Mars radius. And that's the approach that I've taken and we've taken for dealing with planetary missions, and and then Earth missions doesn't matter, right? So like I don't know if I want to get into some of the things that we do, but I'm the principal investigator for the Multi-Mission Geographic Information System, MMGIS, and we built that through, oh boy, it's like always acronyms, the Advanced Multi-Mission Operations System, AMOS, which is part of MGSS. In any case, so we took things like Leaflet, we took things like 3GIS for 3D, and then we built a framework on top of it so that we could map different planets, get the proper measurements, do view sheds with the proper radius, show things in 2D and 3D. And, the Reliant, going open source allows us to be more flexible. It also means that, obviously it's cheap, but more importantly that, we can work with that community, we can build in that community, and we can use open data sets. So, you don't have to, pay the cost of a license, especially for planetary missions, which are usually small, and, money goes to hardware and less to software. Probably true around the world, per se, if you work in that paradigm of building physical objects. But the software is very important. So anyways, but it allows us to be flexible. And also, like, our code is on GitHub, right? So we built this kind of mapping framework, and you can do things like, click on the rover and it shows the rover image. You can then, it automatically pulls up a 3D photosphere view of where the rover is, and you can go into 3D and then look at that same location in 3D. And so having all three of those all together is really important as a geologist, right? Like, I want to look down and see where that outcrop is, and I want to see what the rocks actually look like on the ground, and then I want to show in 3D, and I want to rotate it, and I want to look at the structure. So we, and I'm, so I like to play the joke of, what version of ARC did you start with? And my version, and for the folks, that's ESRI's ARC. It used to be ARC Info, info being the database part, ARC being the spatial part. Version 5.0.2, which was back when it was on a VAX VMS mainframe, and we had the graphics monitors, and it's lines with colors, amazing. Very, very, very old school. So I kind of grew up in that world, right? And I still use commercial software today because it's great. It does a lot of things and has a lot of flexibility. But in terms of like some of the operations we do, the other, like, the one technical part is that a lot of our missions run on Linux. So some software doesn't run on Linux, right? Mapping software. So you have to make decisions about what software supports what OS. But then also it's about speed. GDAL is stupid fast for just cutting things out and doing manipulations. And then things like Postgres or PostSQL are just great for manipulating data and then setting out things that you want, doing very fast spatial queries on things that are, hundreds of thousands and millions of records, which when you get to Earth, interestingly, really becomes a problem. Or at least, there's, you get to this level of images for a mission that are hundreds of thousands of images, and, and the data sets are, gigabytes to terabytes, and now we're talking about, missions that are going to deliver a petabyte of data, which is just mind blowing. Sorry, I had to put in the description of what I'm doing. The mind blowing level of data processing. To me, like, that's like, when you say big data, that is big data. That's just an enormous amount to work with. In any case, tools like GDAL are really fast, and also they're very easy to program. So I will, yes, like, what do you call yourself? Like, would I ever call myself a programmer? No. Do I know how to do some programming? Yes. But, it's Python, it's building scripts, like things that are very fast and easy. But, I can, do things like, just like, I know what this command line should be. I just string a bunch of commands together, and I've got a program, I've got a script. And then I will do things in Python, and that's where I stop. I don't know. I'm not going to go write things in C or assembly or, not even web workers or all that stuff. Yeah. So, I use a variety of things, but open source has been really powerful. And it just like, I can almost give you the year, like 2014 to 2016, like web-based mapping became powerful enough and I would say easy enough that it could be done without having to be a hardcore programmer. And nothing wrong with that, right? Like, but it reached that level. And when you interviewed Vladimir Agafonkin, the founder of Leaflet, and I really enjoyed that interview, because I liked like his ideas of like, this other package is way too complicated. I'm going to make it simple. And, that is like, I feel like the biggest thing for software engineers or anyone who works on mission work, it's like, just make it simple. Because sometimes you have, okay, yes, we have the hardcore computer programmers and engineers, but then we also have geochemists, and we also have geophysicists, and we also have other geologists who just look at images and they just want to map, right? They just want to look at things and browse around, and they all have their specialties and they're all geniuses, right? But they don't know how to map, and you need to give them a map that they can use. And so to me, like Leaflet was such a huge jump of, it's easy, like map, coordinate, go, right? Layer, go. And that was it, right? 3 commands ish. And you could do that. Like even I can write that in JavaScript, right? I had to do it the other day, which was funny, trying to solve a problem for someone who was doing Leaflet in R. And we were just digging into the weeds about like, why I want this TMS tile set render? And like, you have to have both options for doing TMS, not just one. But it was simple enough that you could use it. So yeah, so I think the open source world has just grown to it. It's easy to use, and then it's powerful. GDAL is under everything. All commercial products, right? So I think that just shows that it's excellent software, and it makes us easier to do things, especially for NASA, right? Because technically, JPL is not NASA. JPL, people who work at JPL are contractors for NASA. But we work for NASA. Yeah. So there's a little funny thing about, yeah. So the Jet Propulsion Laboratory is a federally funded research development center, FFRDC. Caltech runs JPL for NASA. So like the buildings and the missions are NASA. The people are technically contractors from Caltech. Like technically I'm a Caltech employee and we do work for NASA, but we are not, like, I'm not a civil employee. So like, when the US like turns off its money supply, we keep working because we just get a chunk of money. We're contractors.
Oh, interesting.
Yeah. So it's weird kind of dynamic. Sorry, I think I lost my thread on where I was going to go with that.
That's okay. There's one thing I wanted to ask you to maybe recalibrate to continue our Dead Reckoning metaphor here. To recalibrate. No, I work with Earth Earth observation images, and I realized, like, slight tangent, that like I use remote sensing and Earth observation interchangeably, but they're not, because it's like Earth observation is a subset of remote sensing. If you're looking at Mars, it's technically not. But so you're totally right. Like we have, we're getting to, I think Planet, the private company, is advertising, and this was years ago, that they have like a petabyte per day. Like we have so much data that I don't know if anybody has estimated like how much images get seen by people. Like what's the percentage? It's probably really, 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 really low. And so I want to ask you about Mars. Like, what is the percentage of images, of data that's collected, that's actually seen by someone? Is that 100%? Is it like, we don't know? Is it like also really low? Have you, like, does someone look at all the images that perseverance and curiosity take?
Probably yes. Let's define some parameters. Like, has at least one person seen every image? Well, does at least one person every day see one of the images, and through all those people have seen all the images that have come down? Short answer is yes, because the number of images is low, right? So I would say even on a busy day, it's probably less than 100 images. So it's a very finite amount. When we get data back from, let's say, like the orbiters, I bet you they're all at least seen once just for quality checks, because it's probably also tens of images, you know, probably not more than 100. So but then there's a different question, right? Which is like, how many other people are going to actually see those images, right? Let's get beyond the engineers. Like, I don't know what Planet does. Like, I don't know if they have someone who manually checks every image, or they just have some unit test and just says, oh, looks like a good image, and gets stored somewhere. So the answer is no. Okay.
Oh, I've worked at an image provider. I
Okay.
worked at a
Okay.
SAR,
Yeah.
like
Okay.
synthetic aperture radar provider. I could tell you, like, there's just too much information.
Okay. Yeah. SAR is a big one now, right? Like, just stupid amounts of data. So after that, I think it depends on the person. I suspect there's a very, well, it's like all about specialties, right? Like, there's people who study Mars, but some study atmosphere, some study ancient magnetic fields, some people stars like big geologic features. There's only a subset who actually look at the surface. And then they're not always interested in everything on the surface. Some are just interested in the geochemistry. So, like, oh, we have the LIBS instrument, which is the laser induced breakdown spectrometer. Right. So it shoots a little laser, hits the rock, it creates a plasma.
Yeah,
and then
that's
we
so
read that.
cool.
We read that plasma and we get a spectra, right? So we know what the rock is. So people who just do that, like, so they don't look at all the images. They just like look at their little. They look, some of them. I bet you they even just look at the spectra. They don't even look at the image. They're like, I don't care. Oh, it's a bright pixel. All right. I mean, it's a bright mineral, I guess. So yeah, it's probably small, but globally, probably every image gets looked at. But then it's like the question of detail. When you have hundreds of images at 25 centimeters per pixel, like, do you look at every pixel? Like, probably not. Same thing like with tile data. Like, how many tiles do people actually look at? It's like less than 5%, I think.
But that's a good rough. The reason I ask is just like, it's basically, I think, a more interesting way to ask like the order of magnitude of data that we create and that we gather on Mars. Like, it's just stupid for the Earth. Like, it's just not even worth trying. Like, it doesn't mean that data is useless. It's like we make land cover maps, and we have change detection algorithms. Like, what you really care about is change. And so if nothing's changed, you don't need someone to look at it. And that's also probably another thing, is like, you don't really need to take an image of an area you've been before. Like, there's not that much that's going to change. Like, I know there's sandstorms, your rover's moving, but like, how much change is there? Let me actually not assume. Like, how much change is there going on Mars that might require taking another image of an area we've already gotten before?
Let's separate a few things out. If you think in terms of geology, like rocks moving, or things that happen like that, like pretty low. I mean, you could say that same of Earth, I suppose, but you've got volcanoes and you have earthquakes, and you have streams which move sediments. Mars is dry and cold, not completely geologically inactive, but pretty close. So yeah, you get one image of an area if you get coverage. That's probably pretty good for most of the cases. If you care about things like dunes or ripple fields, sand moving, depending on the scale, if you care things about the meter scale, like a lot of those things do move every day. So, certain areas you could certainly set up a camera and just like look at that all day and look at movement. Even though the movement is mostly at like the sand scale, hundreds of microns, but big scale features don't move that often. There are a couple of areas where they think like there's these recurring slope lineae. Basically, it looks like there's water coming out of like some spring and going down the side of a crater. We mostly think that's all dry, but those get kind of repeated image every once in a while. The rover, interestingly, because it moves.
Yeah, of course.
We take pictures of it, right?
Yeah.
But yeah, mostly it's pretty inert. If you look at also, if you care about clouds and stuff like that, they have like cameras that do look at the Mars every day, and they have repeat coverage, but they're very big synoptic. I mean, they're worse than, GOES, or it's at that level, right? Like this big, huge kind of hemispheric.
Wait, there are
type
clouds
images.
on Mars?
Yeah.
I didn't know that.
Oh yeah. Yeah. Mars has a very thin atmosphere. It's like
2%, I think.
6 millibar. It's really low, 6,000ths of an atmosphere of Earth. But strangely enough, it's enough. Yeah, they have clouds.
Okay.
They have
Wow.
desert storms, and cyclones, dust devils. And clouds. Yeah, we take. They're super thin. You got to do fun imaging stuff, but we take we do take from the ground. We take time series of the atmosphere to look at clouds and define clouds and look at the structure and see what types they are. Absolutely.
Wow, I didn't know that. That's so cool. I'm gonna go try to find some images of that. This is also like just part of me like nerding out and finding weird fun stuff. I know there's like this pretty famous story of like I forget who lost a lander or maybe an orbiter because there was like a
both
meter and feet conversion that
Yeah.
didn't go right.
Yeah.
So there's this whole thing, but what I wanted to ask is like one of the big differences, again, I don't know if I get the numbers right, but from my memory, the tallest mountain I think is Mount Olympus, and it's like 20 kilometers tall.
Yeah. Oh God, I should know the number. 27.
Okay.
Yeah.
And I was just wondering, like, is there a thing where like your elevation values overflow or something like that? Because on Earth it's about 8 kilometers, I think, is like, and so we have something where there's an assumption the tallest elevation you get is like 8 kilometers, something like that, and then all of a sudden you take it to Mars and you can go up to 22.
Yeah. I haven't run into any hard limits on elevation values, but it does bring a good point. The elevation range on Mars is let me think. It's just about the largest of any planetary body. Interestingly,
all right. So if you take the lowest point and the highest,
just that elevation range, right? That
okay.
It's God, let me do the math in my head. Well, it's like 36 kilometers or something like that.
Wow.
Yeah. It's
so there's
huge compared to
10-kilometer hole somewhere.
Or There's
crater.
There's a Hellas Basin is minus like 8,400 kilometers, something like that.
Okay. Wow. So Earth is 20 because I think Mariana Trench is minus 12.
Yep.
And Everest is 8.
Yep.
So we're past like 32, which you could have a float 32 integer that goes overboard or something.
Yes. It's also a question of the accuracy you want, right? Certain terrain tiles are only accurate to the meter scale, and they're made to fit that data range. They can be 16-bit. But if so like for our mission, right? Like I like to say we go from space to sand. So we care about things at the sand scale, right? A millimeter, sometimes less than a millimeter. So we took that same idea of terrain tiles where you're encoding floating point data into a PNG, so you can serve it out and then create elevation from it on the fly. And we do that, but we've changed our scale range such that we can go down to millimeters, and then also cover the full elevation range. And then actually, it's funny because I had to do this exercise. I'd be like, "Oh, what is the elevation range on all the planets?" And I had to like figure it all out. And Vesta, which is an asteroid in the asteroid belt, actually has a bigger elevation range. I think it's 40 kilometers, something like that. It's huge. So it's really, but it's a small asteroid, but the elevation range is huge. So there's a funny thing that less evolved planets have higher elevation ranges because they don't have the geology to grind down the surface. So you think about all the water on Earth, right? Like, why don't we have a 27 kilometer tall mountain? Because we have water and we have plate tectonics. And so everything's getting erosion, everything's being ground down and pushed under. But not so on the other planets. So Mars, less so, right? Because it may have had an ocean, but not for very long. And if it had plate tectonics, it was really short. So
Yeah, I didn't even think about that, because if you do the ratio of like that variance to the diameter, Mars is also smaller than the Earth.
Yes, it is. It's a
so
third.
It's actually more potato-y shaped.
Yes,
than...
yes, it's a super potato. And I think that's the fun thing about mapping too. It's like all those Earth assumptions, you have to kind of throw them away, or recalibrate, right? Which I think is the fun part.
Have you done other bodies? Like, so we've talked about Mars, Moon. You're doing some work for Earth. Like, we've had some stuff on Jupiter, for example. Like, we don't even have a surface there, or like Venus, where the surface is below, but you have a huge amount of thick clouds. Like, have you worked on other bodies, like on staying on mapping?
I haven't done anything with Venus yet, but they're coming up. I have made some or some made and some borrowed test data sets for Europa, which is a satellite of Jupiter, very icy covered, and there are missions going there. What's it called? JUICE, I think ESA has a mission called JUICE that's going there.
Yeah.
NASA has Europa Clipper. So got some elevation data sets and just pulled some stuff together because I have kind of a demonstration. The other one I did was Enceladus. It's icy body around Saturn, and they have this thing called tiger stripes, which are these rifts that are spewing out material from the inside. And so I was able to I can't remember if I made the stereo data or I found some stereo data, but I created some mapping and just kind of showed we don't care what your planetary radius is, just give us a radius and we'll do it. And so mapped out some of these tiger stripes so you could look at slopes and look at landing on them, and was able to do a little 3D walkthrough and stuff like that.
How do you get stereo images from one of the moons of Saturn?
You wait a lot. So because the orbiter Cassini, it did. I see.
Now.
So for Jupiter we had Galileo spacecraft in the 80s. For Cassini, which is the I think it went at launch early 2000s, but lasted into the later 2000s. So they would basically do these slingshots past Saturn and go out to the satellites and then come back, but they would revisit them. So occasionally they would come back to the same area. So if you were lucky, you got some version of stereo. The other thing they do is sometimes they do photoclinometry, but more like shape from shading. So they look at the changes in the surface shade, and then from that you can dictate out slope, and then you can put on an elevation. So
that's
really,
so cool.
Yeah, tricky stuff when you've only got one image. Then you got to do a lot of math, a lot of modeling to make it work.
So back to Mars, do you have to are you one of the first people that's where's north and where, or are you not even starting to think about coordinate system and it's just mapping basic?
Just mapping basic. That was decided more in the actually I don't know if I have an exact date, but let's just say 60s or 70s. I see. Okay. They've picked probably even before that they picked what was north. I think later in terms of what the coordinate origins was a little bit later, but certainly by the 60s and 70s, because they had orbiters fly by, so they had enough of the planet to start to map and pick features, and then they really needed at that point. Then they needed a coordinate system because they wanted to have the spacecraft go by and come back again, and okay, I want to target that volcano. Well, where is it? All that type of stuff.
So is Mars the only other, and the Moon, the only other two bodies that we have proper coordinate systems for?
No, they all do.
Okay.
But the accuracy varies depending on what images we have.
Of course.
Right? Titan, we have global coverage now, For the most part, different resolutions, but I think some of the smaller moons, less so. But they all basically, once you know the spin axis and you have enough images to pick an equator, you pick equator. Yeah.
What are some of your like either missions or just mapping related projects that you're excited about? Because this like continuously changes. Like
Yeah.
we keep sending more things. Like is there anything that you're looking forward to?
The one that I'm most excited about is probably Venus, because we're going to send 3 spacecraft. On the NASA side, we're going to send Veritas and Da Vinci. On the Europe side, oh God, I should know the name. It's not Endeavor.
That's a bit of an overused term name for like spacecrafts.
It's like
I didn't know that. I didn't know we were sending a new.
Envision. That's it.
Okay,
Envision.
I didn't know we were sending new probes to Venus. I know, like, if you've worked in the SAR world, like people know about Venus because we've mapped the surface of Venus with SAR, because the atmosphere is so dense that you can't do anything optically. Well, Fred, this was a really cool conversation. Just like how I like starting it with the same question, I like ending it with the same question. So I was looking at your bookshelf earlier, and the reason is also because I do like asking for a book and a podcast recommendation. So I know you read, so I'll ask about that. And then if you listen to any podcast that there's anything that you think is worth sharing, there's a couple of reasons I like asking for that. The first is I think a lot of like books and podcasts really travel through word of mouth. I'm always looking for new stuff. And it's just a fun, different way to know a little bit more about people as well. So yeah, if there's any book that you think is interesting, science fiction, nonfiction, anything, doesn't really matter, that you think is worth sharing, and then same thing for a podcast.
The 3 body problem books.
Yeah, you have the trilogy right there, right?
Yes, I do. Yeah, by Jian Liu. I will say after reading it, I was a little bit depressed, and I had to think about what the book actually was trying to say. Have you read it?
I've read just the first one.
Okay.
For now.
Okay.
And I can wholeheartedly recommend it as well.
Yeah,
it's some of the best science fiction.
Yeah. I know the author said something like, the technical part of the science is actually the interesting part, or something of that vein of like, like people want to hear that, like they want to understand things, and sometimes it's the details that are most interesting to read, and so I like that idea that it doesn't have to be this made up, we put in the phase modulator and like, no, you can actually, the real science is really cool. So I like that idea, even though his book, like, oh boy, I don't know, because I think about space and future civilization and stuff like that, and it was a tough read, just like the conclusions to it. Anyways,
I see you have like Andy Weir's The Martian as well, like on the hardcore science fiction. That is also an amazing read and very on topic.
Yes. Andy Weir, interestingly, this is a really weird story, but right before I was coming to JPL, I found his blog that eventually became the book. And I was reading it. I'm like, oh, that's really cool. Yeah, you know about rovers and stuff like that. And I emailed him and I said, hey, sorry, this is going to sound very braggy, but I was like, hey, if he doesn't have communication, there's a rover he could go to and get the antenna. And he wrote me back and he said, funny you say that. And we had some other conversations about details.
So he had that part of the story already.
He hadn't posted it yet, but so he was still developing his ideas. So that was kind of fun. And then he came to JPL at one time. I got to meet him, which was great.
The book was originally like just his blog, and then turned into a book.
Yeah, turned into a book. Yeah. So it's always interesting. But there's also the other problem is like knowing too much. Like there's a part where it's like, oh, I dig up, like in the movie, it's like, oh, I have to unbury the rover. It's like, no. We have pictures of it. We know it's not buried, but it's all right. It's a story over details sometimes. Yeah, I think that's things that I've read recently. I don't have any podcast recommendations. I'm sorry.
That's fine. No
I
worries.
don't listen to a ton of them. So I'd be just leading you astray.
There's one last question that
Sure.
is just kind of a fun thing. I've been around like people who work on Mars related missions, and so we talked about it. There's this notion of I don't know if we called it up, but there's Souls, which is like a Martian day,
Yes.
which is I forget, like 32 hours. I'm not exactly
No,
sure.
no. I always do it the wrong way, but it's either 23.42
Oh, okay, yeah, it's a
or
tiny.
it's 24.42. One of the two. I can't remember. It's a little bit shorter, a little bit longer. Yeah.
Yeah. And so, but that kind of adds up over time. And so,
Yes.
what I do know is that people who worked on that have 2 watches. Do you have 2 watches?
Um, I do not have 2 watches. That was done for a very specific mission. The Mars
Okay.
Exploration Rover teams, Spirit and Opportunity. I do not. However, I have survived 3 Mars times, and Mars time is the beginning of the mission. It's usually 90 days where you work on a Mars day.
Oh, right.
So, today, Mars morning is 8 a.m. Tomorrow it's 9 a.m. Next day it's 10 a.m. So you have to shift your work schedule. To
Right.
some point, your morning starts at 2 a.m. or your morning starts at 4 a.m. You do that for 90 days because it's like the concentrated time of the mission where you want to get the most out of it, right? To have success. So yeah, it's a little rough. And the worst part, there's Mars time, but then there's Mars orbiter time, right? So you can't. So basically, the rovers, we talk to like an orbiter, and that talks to the rover, and then the rover talks to the orbiter, and then sends it back. So depending on when that orbiter comes over to catch the data from the rover, that data comes back at other times. So now it becomes, instead of just like it's 8, it's 9, it's 10, it's 8 a.m., it's 10:30, it's 9 a.m., it's 1 p.m., it's 7 a.m., it's 4 p.m. Like it would like rotate but go back and forth, and that was just horrendous, horrible. But nevertheless, we all do it. It's kind of a trial by fire, badge of courage. Pick your meme on that. That we all survive, but it's tough. Actually, like definitely like getting used to it for the first 30 days, and also like you can be like at home with your family, but you're going to sleep, they're waking up. Meals are very weird. I definitely spent the time. We went walking in a park, and I don't know if I remember half of it because it was like 2 a.m. for me on Mars time, and it was 11 a.m. during the day. It was tough, but fun times. Yeah.
Well, I think that's a great anecdote to end it on. Thank you so much for your time. This was such a fascinating conversation. This was so cool. Thank you
Thanks,
so much.
Max. I appreciate the questions. They're really good.
Hey, thank you so much for listening to this conversation. I wanted to take a moment to thank the sponsor of this video, but also all the people who financially support me on Patreon. If everything goes well, these conversations should feel and sound seamless and effortless, but there's a lot of work that goes behind the scenes. I try to research and prepare these as much as I can to know who these people are and what makes them interesting and what would lead to a good conversation. I'm incredibly thankful to all the people who support my work on Patreon, meaning I can do a little bit more of it. This podcast started out as a way to learn more about the people in this industry, but I've also started making educational content on another YouTube channel that I'll put a link to in the show notes. And I want to make more content explaining how satellite images and maps work to a broader audience, as well as continuing to research the guests for these podcast episodes. So, if you value the work that I do, I'd like to ask you to please consider supporting my work on Patreon. There's also some behind the scenes of how this podcast is done and some of the work that I'm doing for these educational videos if you want to learn more about how I do all of this. Either way, thank you so much for all of your attention and your time. I really appreciate it, and I hope you get value from these conversations. Thanks.